Alright, this video is on the objective complete the steps of a one mean hypothesis test with population standard deviation as the SD known. And it's the critical value approach, right, where you find critical values and set up a rejection region and then see if your test statistic falls in that rejection region or not. Alright, so this is a video, this is number one, right? This is the first video I'm doing on a question related to this objective. Now this is it. I mean, we're putting all the steps together. We're going to identify the claim, set up the hypotheses, see if it's a right-tailed, left-tailed, or two-tailed test from that. Then identify the significance level, alpha. Then we're going to look at a sample. Find the test statistic for that sample. Then we're going to find critical values, right? Maybe one or two of them, depending on what kind of tests we're doing. And then, set up a rejection region and then see if our test statistic falls in that rejection region. And then we're going to decide if we're going to reject the null hypothesis or not. And then we're going to state our conclusions. All right, so all the steps put together, one after the other, in this one problem. All right, so let's take a look. So again, if you want to see more stuff here, click on more instruction, look at their videos, their notes, their examples, and hopefully that helps you out. All right, so here. And I'm going to go to some paper with this, of course. A recent article stated the average unemployment rate in a particular city was 3.9%. An economist would like to test the claim that the average unemployment rate is small in smaller towns outside the city is different than 3.9%. To test this claim at the 1% significance level, the economist collects the following data on a sample of 31 smaller towns and records their unemployment rate. The following is the data from this study. All right, so sample size, again, he took 31 of these smaller towns outside this city that was mentioned. The average unemployment rate for these towns is 4.2%. Now, from past data, it is known that the population standard deviation is 0.8%. So sigma is known here, right? The value of the population standard deviation. And if sigma is known, that means we're going to, our test statistic and our critical values are going to be eventually z-scores, right, from the standard normal. All right. So I'm going to go to some paper and write this stuff down here. And we'll go through the steps of a hypothesis test. So one is identify the claim that's being made, the claim that's being tested. Now, off to the side, I'm going to have, this is about average unemployment rate here. I'm going to have mu, usually represents a population mean. This is the average or mean unemployment rate for all these smaller towns. For all smaller towns, or small towns, I'll say, or for just all towns. Oops. Average unemployment rate for all towns. Now the claim being made is that the average unemployment rate in smaller towns outside the city, right, for all this, for all of them, is different than 3.9%. So the claim is that mu is different from 3.9%. Let's write 3.9. Notice again, this doesn't involve equality. So when I go to set up my hypotheses, right, the null hypothesis, the alternative hypothesis, the claim is going to be represented by the alternative hypothesis. Right, the alternative never involves equality. So the claim is in the alternate or alternative. And remember, once one of these is set up, the other one's the opposite. The opposite of not equal to is equal to. And don't forget, we are going to assume that the null hypothesis is true, and then decide whether or not we want to believe that. All right. So we're going to assume that the average unemployment rate for all these smaller towns is 3.9%, and then based on our sample and test statistic and all that, we're then going to decide whether or not we want to believe that or not. What do we reject the null hypothesis, or do we not reject it? Okay. And then also, looking at the alternative hypothesis that mu is not equal to 3.9, different from 3.9. This is a two-tailed test then. So when I go to find critical values later, there are going to be two of them. Right? It's not just a right-tailed or a left-tailed. All right, so claim is formed, a claim is identified, hypotheses are formed. Then you have the significance level for the test is identified. Now, if it's not mentioned, if a significance level is not mentioned, it's reasonable to assume 5%. That's a reasonable significance level for most tests. But it was mentioned here. They said at the 1% significance level. So alpha equals 1%, or 0.01. All right. Then after this, we look at our sample. Now, so you took 31 of these smaller towns, right? So n equals 31. And the sample mean, right, the average unemployment rate for these 31 towns was 4.2%. And sigma is known. Right, they told us that the population standard deviation, sigma, is known to be 0.8%. Now, because sigma is known, by the central limit theorem for means, the distribution of sample means for all samples of size 31 would be approximately normal, with a mean of mu x bar, standard deviation of sigma x bar, where remember the mean of the sample means is the mean of the population. But what is that? Well, we're assuming that the mean of the population is 3.9%, right? We are assuming that the null hypothesis is true, and then going through and deciding whether or not we want to keep that. Do we not reject it or reject it? So the mean of this distribution of x bars is 3.9, and the standard deviation of the x bars, remember, was the standard deviation of the population divided by the square root of the sample size. So this was 0.8 then, right? That was what was given to us, divided by the square root of 31. And I can put that in the calculator. I'll just leave it like that for now. I'll punch it in the calculator. And we'll get an approximation of the standard deviation, and then I'll draw a little picture of a normal distribution. Alright, so pulling a calculator up here. This is 0, turn it on. Alright, so 0.8 divided by the square root of 31. So the standard deviation for the distribution of sample means for all samples of size 31 is approximately 0.14. Alright, so I'm going to draw a little picture. Here's a number line representing all possible values of the sample means for samples of size 31, all possible values of x bar. Said it would be approximately normally distributed, right? So this symmetrical bell shape curve. Underneath the peak is the mean. And we said a second ago, we're assuming that the mean value is 3.9, right, from the null hypothesis. And under these inflection points, remember the inflection points should be about, should be one standard deviation above and below the mean. So this is approximately 4.04. And over here, this is approximately 3.76. Right. And remember, within one standard deviation, there's approximately 68% of the area under the curve, but that's neither here nor there. That's not helping us. All right, now, what do we do with this? So, we're assuming the mean is 3.9. We took a sample. They took a sample, and the average was 4.2. Now, let's see where that falls. Now, that'd be like over here. Right? There's 4.2. Here's our x bar, right? Our sample mean. Now the question is that too far away from the middle for us to like that assumption? Right? Is assuming the mean is 3.9 a bad assumption? And if this is too far away, if this is too many standard deviations away, then yeah, we'll say it's a bad assumption. We'll reject the null. But if it's not too far away, right, if it's not that many standard deviations away, then we'll say it's okay. It's probably okay to keep assuming that the mean is 3.9. We won't reject the null. All right, so that's where my z-scores come in. Right, we're going to determine, talk about how far away this test statistic, this 4.2 is, and this is the calculation of the test statistic, where we change everything to z-scores. Right, this is a normal distribution. So we're going to normalize this, right, meaning change it to the z distribution, the standard normal. So here's z, and then normal distribution. And my bells look different every time, I apologize. Then the z-score of 3.9 would be 0, right, because that is the mean. And the z-score under these inflection points, would be 1 and -1, right? Because that value is one standard deviation above. This value is one standard deviation below. But the big question is, what is the z-score of our 4.2? Right. So I'll call that z-test. All right. So this is our test statistic. Test statistic. So it's, again, just the z-score of our sample mean. So first of all, how far away is it? So I take 4.2 minus 3.9. And then we divide by the standard deviation. Now remember, the standard deviation for this distribution was this 0.8 divided by the square root of 31. And I'll punch this in and round. Now, 4.2 minus 3.9 is 0.3. So 0.3 in the numerator divided by, and then I'll put this in parentheses in the denominator. We got 0.8. Oops. You know what? I'll just use the previous answer. That previous answer is my standard deviation. All right. So it's about 2.088. So what this tells me, 2.088. What this tells me is that our sample mean is 2.088 standard deviations above the mean. So this sample mean is just a little more than 2 standard deviations away from 3.9. And that's kind of far away. Now, is it far enough away to where we're going to reject 3.9 as our mean, where we're going to reject the null? Well, that's where the significance level comes in these critical values. All right, so now that the test statistic is found, now I go and find the critical. Now this is a two-tailed test. So I find two critical values, one on the right and one on the left. So again, we're looking at the z distribution, the standard normal. Right, mean of 0, standard deviation of 1. So again, I got 0 in the middle here. Now, again, being two-tailed, and alpha equals 1%, 0.01. I want to find values. I want to find a value to the right and a value to the left on the same distance. It's symmetrical, so that the area to the right of this value plus the area to the left of this value is 1% total. So that means I want what's the z-score with an area of 0.5%, 0.005. And over here, what z-score has an area of 0.5%? Right, that way it makes a total of alpha, a total of 1%. So this z-score we're looking for is the z-score with an area of half of alpha, right, 0.005 to the right. That's the z with a subscript of 0.005. And then this value over here is just the opposite of that, so negative z-score with an area of 0.005. So I'm looking for this. What's the z-score with an area of 0.5% above it? Now you can use the table to find this, or I can do a calculator. Remember that inverse norm. Right, go to inverse norm. Now, when they ask for area here, that's the area to the left. Now, if I'm looking for the value with 0.5% to the right, that's 99.5% to the left. So I enter 0.995 here. Mean 0, standard deviation 1. That's 2.576 if I round. So this is 2.576, and this is negative 2.576. And this gives us our entrance to the rejection regions, right? This is a rejection region over here. This is a rejection region over here. Let's say reject. And if our particular sample, if our test statistic falls in those regions, we're going to reject the null hypothesis. We're going to say, oh, the mean probably isn't 3.9 because our first sample ended up being so far away. But if it's between these, then we'll be like, okay, I'll keep the null. The mean. It's okay to still assume that the mean is 3.9%. Well, look at our test statistic, right? It was 2.088. That is not bigger than 2.576. 2.088. Our test statistic is here. Here's the test stat. And that's not in these rejection regions. So, looking at this picture, I'm not going to reject the null. We're going to fail to reject the null. We don't reject the null. And the null was this. The mean was 3.9. Right? So we're going to keep that. That means, now if we're not rejecting the null, that means we're rejecting the alternate, right? And the alternate was the claim. So we do not support the claim. All right, so I would not support this claim that the mean is not 3.9. I would support the fact that it probably is 3.9, or at least I can say with reasonable certainty that assuming that the mean is 3.9 is okay. All right, so that was a full hypothesis test. Now back here, let's go through it and fill in all the stuff they asked for. Now they want here remember the null hypothesis was that they're equal, then not equal for the alternate or alternative hypothesis. And I'm sure they'll have me do more because it's completing all the steps. All right, I don't know why these are 10. There's a typo here. It should be 3.9. Then they have you fill in these pictures. So remember, this is a two-tailed test. So it was a two-tailed test. The sample size was 31, right? It took 31. The n was 31. I guess before I do that, the significance level. Remember, the significance level was 1%. The sample mean The mean for that sample of 31 homes was 4.2, right? The X bar. 4.2. Come on. There we go. The mean of the population, right? That's the mean that you're assuming from the null hypothesis. That was 3.9. And then the standard deviation, they told us sigma was 0.8. You see what it's doing here? It's moving our test statistic. Now I said the test statistic was 2.088, which would be 2.09. Remember all the calculator work I did? It's 2.009. And look where the test statistic falls compared to these rejection regions. See the critical values are at 2.58. Oh, I said 2.576. That'd be rounded to 2.58. There's the one rejection region with an area of 0.5%. The other one over here with an area of 0.5%. And our test statistic does not fall in those rejection regions. So again, the test statistic, now they're just having you enter the test statistic as it looks in the little picture here. So test statistic 2.09. The critical values, I think they want you to enter plus or, yeah. So if there are two critical values, use a plus or minus symbol. Right. So I got plus or minus symbol here, and then it was 2.58 on the picture. Right. 2.58 on this picture. The entrances to those purple regions. Okay, great. Again, I did all this by hand, but they're having you do it. Here again. Here's how you calculate your test statistic, right? They rounded it to 2 decimal places. They found the critical values the same, with this the same way. And then, based on the analysis above, which of the following statements demonstrates the correct interpretation of the results for this hypothesis test? Remember, I said that we weren't in a rejection region, so we don't reject the null. We fail to reject the null. Now it's one of these two. And then the rest of it is, do we support the claim that the mean is not 3.9? It is different from 3.9. Remember there, I said if we don't reject the null, then we're not supporting the alternate or the alternative. And the alternative was the claim. So we're not supporting the claim. So we fail to reject the null. There is not strong evidence to conclude that the average unemployment rate of smaller towns outside the city is different than 3.9%. That was the alternative hypothesis, and we're not supporting it because we're keeping the null. And there's your conclusion. And again, read through, answer explanations, please. Especially if you got it wrong, right? See, hopefully you can figure out where you went wrong, and next time you see a problem like that, you can go back and fix it. And I think that's it. That's actually the conclusion. You completed the whole hypothesis test. All right. So hopefully that video helps you when you're going through your own steps in a hypothesis test. I'll do one more on this, and thank you very much for watching.